Welcome folks. In this lecture we are going to introduce op-amps to you. Op-amps are also called operational amplifiers. Op-amps are considered to be one of the most fundamental blocks in analog engineering, basically in electronics. It is not a simple component. It's not just a resistor or a transistor or a diode. It is not a single component but a module. A typical op-amp contains anywhere from 10 to 20 transistors or more. Now, why op-amps are important? Because op-amps as a module are used in many applications, including amplifiers, including filters, we call them active filters, including mathematical operations such as integrations, derivatives. They also used in things like rectifiers, high precision rectifiers. They are used as a fundamental blocks in something that we call digital to analog converters and many other applications. So op-amps are very fundamental modules that are used in electronics, and that is why we stress op-amps and we introduce the op-amp as a concept early on, like in simple courses like Circuit 1 and in Electronics 1, and of course beyond. Basically, in advanced electronic engineering, the concept of op-amps becomes extremely important as we start to increase its bandwidth and its frequency response and its accuracy and its slew rate performance and its input offset currents and so on. So those things will continue to improve as technology continues to evolve and advance. So what I'm going to do in today's lecture is I'm going to introduce op-amps as an introductory level topic, but from a different perspective. And I hope that this will make a deeper understanding to the students when they follow and understand and study op-amps. And I think that in today's presentation will be much more efficient and much better for students to understand. So let's start. If you look into the op-amp as a symbol that we see, then you can see that the op-amp has three terminals, three legs. One of the legs has the plus sign, so this is going to be an input. We call it non-inverting input. And the non-inverting input, we are interested in two things in it. First of all, there will be current going through it, and this current usually is very small, that we can assume it is zero for now. And the voltage at that leg, we're going to call it V plus, because it's going into the plus sign of the op-amp or the non-inverting input. The other leg has the negative sign. We call this leg the inverting input. And in this inverting input, also there is a leakage current going in. This leakage current going to be very small, so we're going to assume it is zero. So we're going to say that the current going through it is virtually zero. So the designer, when he designed the op-amp with the transistor components inside it, he wanted to make sure that this current going to be small. And we're going to understand why those requirements become important. So the voltage at the inverting input, we're going to give it the sign V minus because it is connected to the inverting input with the negative sign. The third leg is basically the output voltage. We're going to call it V out. The question is, how does the op-amp work? And the answer is very simple. The op-amp will take the differential input voltage, which is basically the difference voltage between V plus and V minus. So we're going to define a term, we call it the differential input voltage. And the differential input voltage is basically going to have the subscript Vd, and that will equal to V plus minus V minus. So what that means is the differential input voltage is basically the voltage difference between the plus leg and the negative leg, between the positive leg and the negative leg. So the voltage difference between the non-inverting input and the inverting input is called the differential input voltage. And the output voltage, V out, is basically going to be some factor A multiplied by the difference voltage V plus minus V minus, which is the same as saying that it is A times VD. What's very interesting here is that this number A, we call it the gain of the op-amp, or basically we can also call it the open loop gain. So there is two terms for it, the open loop gain or the gain of the op-amp. So far so good. We said that the op-amp is nothing but a simple component that has three terminals, three legs. The two legs, V plus and V minus, are called the input terminals, and the other leg is the output terminal. The way the op-amp works is that it takes the difference between the inputs and it multiplies by some factor A. A very simple example, we can say that if A equals 10, then V out will equal to 10 times the difference of the input voltages V plus minus V minus. And if A will equal to 1000, for example, then V out will equal to 1000 times V plus minus V minus. Clearly there is a problem here that you say that if I wanted to have a gain of 10, then we are going to design a special op-amp with a gain of 10. And if we want to have a gain of 1000, then we have to design a special op-amp with a gain of 1000. Now the problem is the op-amp comes in as a complete module, and this module can be a complete chip by itself, right? Like for example this chip that you see here, or it can be a module within a bigger system, and the big system comes in a chip. So what happens is, if we're going to design an op-amp for each particular gain, this becomes a very expensive process. So what we need is we need to have some general purpose op-amp, one op-amp that can be used for multiple applications, and then that becomes economically feasible and used for engineers to develop their system. Now, to understand how the op-amp works, I'm going to give you 4 simple examples. And after we understand those 4 examples, we can move on and start to look into the real applications of using op-amps. So let's look at the first circuit. And in the first circuit, what I'm going to do is I will have the op-amp as shown here. And then I'm going to come to the inverting input, that is the minus sign of the input. And I'm going to ground it. So this will read basically 0 volts. And then I wanted to measure the output, V out, if I'm going to apply an input signal to the non-inverting input. So we're going to call it Vs. And let's assume that the gain is given, and the gain can be any value A. So the value of A is given. Basically, V out will equal to A times the differential voltage. So the differential voltage here is going to be Vs minus the other voltage, which is ground, so it will be Vs minus 0, which is basically A times Vs. Well, this is nothing new, it's very similar to what we said before, but let's look at the second circuit. In the second circuit, I'm going to reduce the effect of the input voltage. I'm going to negatively reduce the input voltage. So what I will do is I will come to the inverting input and I will add some value to it. So let's say that this value is going to be 1/2 times the input voltage Vs. It can be any value, it doesn't matter. We're going to use 1/2 here just to show you the power of the inverting input. And then we're going to have Vs at the non-inverting input, that's my input signal. And now we're going to say that let's find V out. According to the equation, V out will equal to A times Vs minus 1/2 Vs. So this basically becomes 1/2 A times Vs. So what's the difference between the first circuit and the second circuit? Why did I give you those two examples? Well, in the second circuit, the output voltage have been reduced by a factor of 2. Because of that, then what is important for us is that when we add a voltage to the inverting input, the out is decreased. So the inverting input negatively affects the output voltage, reduces it. And this is very powerful observation, is that by increasing the negative voltage, we can reduce the out. So why this is important? Because let's look at this example. Let's say that I'm going to apply Vs to the input, but from the output, I'm going to feed all of V out back into the inverting input. The inverting input becomes V out. So this is called negative feedback, because I have fed the output all the way to the input in a negative way. Now the effective voltage becomes Vs minus inverting input. Then it is a negative feedback because the output have been negatively fed back to the input. So it's a negative feedback. This circuit called a buffer or a unity gain amplifier, and this circuit is very important because I have fed all of the output back to the input. This is the strongest negative feedback you can have, when all the output is fed back to the input. What kind of a gain do I get, or what kind of V out do I have? So let's apply the equation. V out will equal to A times V plus minus V minus, which is equal to A. I know V plus is nothing but Vs minus the voltage at the inverting input, in this case, is nothing but V out. So now I can play with the equation a little bit, so I can say that V out will equal to A times Vs minus A times V out. I can bring minus A times V out to the other side of the equation, so I will have V out plus A times V out will equal to A times Vs. And now what I can do is I can factor the V out out. So I will have V out 1 plus A will equal to A times Vs. And I can say that V out will equal to A over 1 plus A times Vs, which is nothing but 1 over 1 plus 1 over A times Vs. All what I did here is I divided by A on the top part and in the bottom part, so I will end up with this form that I have. And this is very powerful equation, because under this condition, the output voltage can change based on A. Let's say, for example, if A is very small, like let's say that's 0.1, then V out will equal to 1 over 1 plus 10 times Vs, which is basically going to be 1 over 11 times Vs. Now let's say that if A will equal to 1, then V out will be 1 over 1 plus 1 times Vs, which is 1/2 times Vs. Now let's say that A is very, very large. So somebody will say, how large is it? So I can say that, let's say that A will equal to, let's say, just 1,000, then V out will equal to 1 over 1 plus 1 over 1,000 times Vs is basically gonna be roughly 1 over 1.001 times Vs, which can be approximated to be Vs. The conclusion here is that if A is very large, then V out is roughly gonna equal to Vs. And this is a very powerful observation. If we feed all of the output back to the input and A is large, then the output voltage gonna equal to the input voltage. V out is equal to Vs. Very, very, very powerful observation. So the question becomes, why is this very important if all what I can get at the output is basically the input voltage? Well, even though this circuit is important when we wanted to buffer the input from the output, when we wanted to separate the input from the output, but more important than that is if we don't feed all of the output, only portion of the output is fed back to the inverting input, then I'm gonna get a higher gain. This is the intuition, and let's work it out and show you what do we mean. So let's look at the op amp. Here is our op amp, and this is the fourth circuit that we're gonna look at before we come up with the conclusion. So here is the op amp. I will have Vs at the non-inverting input. Here is my output voltage, and now at the output I'm going to have two resistors in series like this. So the bottom one we're gonna call it R1 and the top one gonna call it R2, and we are interested in the voltage in the middle between those two resistors. We're gonna call it Vx. Clearly those two resistors are in series and Vx going to be less than V out. In fact, that we can say that Vx using the voltage divider is nothing but R1 over R1 plus R2 times V out. So basically what that means is Vx is only portion of V out. Now I'm going to feed this Vx back into the inverting input, and I wanted to stress that the current going to the op amp is roughly 0. It's very small. And this is why when we design the op amp, we make sure that the current going into the op amp is very, very, very small, because when we connect the feedback through it, we don't want any current going to the op amp. Ideally, we assume it's 0. In reality, there is very, very, very small current going into the op amp, and we're gonna assume it is 0. So to keep the story short, basically we say that not all of V out is fed back to the inverting input, only portion of that output voltage is fed back into the inverting input. And now let's analyze the circuit and see what's V out going to be for a given Vs. So we know that V out will equal to A, that's the gain of the op amp, times V plus minus V minus. But V plus here is basically Vs, so we can say that V out will equal to A times Vs minus, and the negative voltage and the inverting input voltage is basically Vx, so we can say that minus Vx. But Vx is also given as a function of V out, then we can state that V out will equal to A times Vs minus A times R1 over R1 plus R2 times V out. I can take V out term to the other side of the equation, so I can say that V out plus A times R1 over R1 plus R2 times V out equals to A times Vs. On the left hand side of the equation, I can factor V out of, so I will say that V out multiplied by 1 plus A over, and if I divide R1 on the top and the bottom, I will have 1 plus R2 over R1, and that will equal to A times Vs. Now I can solve for V out, so V out will equal to A over 1 plus A over 1 plus R2 over R1 times Vs, and if I multiply the top and the bottom by 1 plus R2 over R1 and divide by A, then what I will have is 1 plus R2 over R1 on the top divided by 1 plus R2 over R1 plus A, and this thing can also be divided by A, because I divide by A on the top to get rid of the top A, then I have to divide by A at the bottom, times Vs. So now we can say that V out will equal to 1 plus R2 over R1 over 1. Here I'm going to divide the A by the A, becomes 1, and then I will say plus 1 plus R2 over R1 divided by A, and this is times Vs, and this is the output voltage as a function of the input voltage and the resistors R2 and R1. Now let's look what happens if A is very large. If A is large, then V out will equal to 1 plus R2 over R1 over 1 plus R2 over R1 over A. But A is large, then this term becomes 0 times Vs, which is nothing but 1 plus R2 over R1 times the Vs. So if A is very large, the gain of the circuit becomes 1 plus R2 over R1. But what's important about this perspective, the way we showed you this circuit, we have two important aspects from it. The first one is we understood that we fed the output back to the input, and in this particular circuit we fed portion of that output into the input, and we have to force the current into the op-amp to be 0 or very small, that it is negligible. And this is part of the designer who designed the op-amp. The people who designed this op-amp circuit need to guarantee that the current is very small.